Okay, can everyone hear me? Yeah, let me know if they can hear me online as well. So, like John said, my name is Tyler Morgan. You've probably seen me around yesterday. I'm one of the people that got to be here because the government didn't shut down. And just to give you an idea of where we come from with NIH, etc., this is a picture I took from the plane on the way up here. But if you ever fly out of DC National, you always fly directly over NIH and get this really cool view of the big building. And if you know where to look, then you can actually even see our imaging center, etc. So just to start things off, what are we going to hear about today? This is basically just our schedule as a series of topics. So we're going to hear about cortical segmentation. We're going to hear about functional and structural registration. We're going to hear about how to do distortion correction, because this is an issue that comes up in a lot of high field images. High resolution data processing from John. As well as some topics on denoising, physiological noise as it relates to cortical layers specifically, and then what do we do about partial volume. A lot of this is, of course, kind of jargony to our field of layer fMRI, but hopefully by the end of the day, everyone will be completely expert on a lot of these different things. But my job this morning is to give us an idea of kind of how does this relate to the big picture of what it is that we're trying to do with some of the layer fMRI studies that we do. So to that point, laminar fMRI data analysis essentially has one primary goal, or at least a lot of our studies fall into this category of having this goal. And that's that we want to take our heaps of beautiful high-res brain images that we got yesterday from Saskia and Renzo. Hopefully everybody went home last night and scanned really beautiful data, and we'll just start from there. So we're kind of moving beyond where we were with just the acquisition, and now we're sitting at our laptops and actually thinking about like the scientific problems that we intended to start with, or we intended to do in the first place. And for a lot of us, this basically is the goal of finding an interpretable layer profile. And different people have different hypotheses about what layers should be doing in their particular tasks, etc. This is kind of this very classic pot of gold that a lot of us are looking for, this double peak structure. But importantly, there's this arrow in between. And this is obviously magic that you get in between these two things. But I think it's important to break it down in a way where it doesn't seem like magic anymore. It doesn't seem like something that like you see in papers, but you can't figure out how to get there. It's like, these are steps that we can really get to. And I think it's also really important to kind of just think about what that layer profile is actually telling us, because as much as I commonly look at it and try to think about it in a whole bunch of different ways, really this is just a relationship between two different things. And it's first, the anatomical structures that we care about in MRI. And that's our x-axis here. And so we're basically trying very, very hard to very accurately define what each layer is in terms of how close a particular voxel or different measurement is to the white matter or to the edge of the brain, so the CSF. And then on the y-axis, of course, we have this whole slew of questions that we can ask when we're telling people in the scanner to do particular things, but really it just comes down to the type of activation or information measure, etc., that we get from our functional. And so this is really just telling us the relationship between our anatomical types of imaging and the functional contrast that we're trying to look at. So this means that we have two types of magic to perform when we're doing our layer fMRI studies. This essentially means that we have to figure out how to deal with understanding the anatomy of what we're looking at a very, very precise level, high level, I guess. And this can come in a whole bunch of different fashions. One of the ways that we're going to think about this today, well, we are going to have two different talks today that are going to relate to how do we process anatomical data in order to kind of get us well on our way to understanding what layers look like. The first that I'm going to point out is that we're going to hear kind of from Daniel and Doug about how to deal with this at the whole brain level. And this is a huge challenge. And I mean, for a whole slew of different reasons, but getting this accurate map of where the inside of gray matter and the outside of gray matter over the entire brain is tough, obviously. And oftentimes this can also kind of relate to how do we deal with these problems in 3D. So how do we deal with the fact that this is not just a big block of data, but this is actually a 3D object that we look at in the scanner, and we need to think about it that way. Next, we're also going to hear a little bit about what we do when we don't necessarily care about the entire brain, or we've thought about our acceleration strategies in terms of cutting down the amount of information in the brain that we're actually looking at, not necessarily doing acceleration through our acquisition, but just trying to only look at a small part of the brain because maybe it'll help us. So from Farouk, we're going to actually hear a little bit about the ways that we can look at data in very, very small areas, and what are the tips and tricks that we can kind of think about in terms of making sure that that process happens. Because the process of segmenting a brain when you're only looking at a small patch of it are very different than what we see at the whole brain level. Because one of the advantages that we really have in neuroscience, or in human neuroscience in general, is that despite the huge amount of variability that we see across individuals, everybody's brain kind of looks the same. So we can take advantage of that in some of the tools that we saw in the previous slide. But here, looking at very small patches is often a little bit more challenging. We can have a little bit more intuition about it because oftentimes we look at the same brain area over and over again and try to get an idea of what it is. But at the same time, a lot of these measures look very different because you're trying to do something that is not always the standard. So, and in that same vein, once we look at these different areas, how do we actually look at cortical depths? We'll hear about this both today and tomorrow, I believe, but then actually model those patches individually in ways that we can make sense of, again, as a 3D object. And then, of course, there's also this whole other side of things, which is our y-axis of our laminar plots, where we need to take something like what we saw yesterday and just saw John highlight again, that we want to be able to use whatever data it is that we are capable of acquiring. And no matter what it is, try to get something useful out of it. So even though what we might see come out of the scanner on the left side looks like, how am I ever going to approach this? We need to get to the point where we can actually look and see and highlight the things that we see on the right, which is the tasks that we're doing, what the neurons are actually related to as we're going through this experiment. And so in this next slide, I potentially am going to age myself a little bit, but I'm going to just talk not necessarily about the specifics of layer fMRI, but just what it looks like to actually do a pre-processing stream and data analysis stream for fMRI in general. And the reason that I'm going to highlight this is, one, we can kind of show where things change, but two, when I started doing layer fMRI, I didn't know a single person who was doing it that didn't come from a background of doing regular fMRI, what we'll call regular fMRI. And I think that that's changed over time. I come in contact with more and more students that have never actually done a project on 3T or potentially are coming directly into the field of high field imaging. And so we just sometimes need a reminder of like a lot of the tools that we use, they're adaptations or ideas that have been in the field for a very, very long time. So we start with our time series. This is going to be a 4-dimensional just image object. And then as we saw in the previous slide, oftentimes we see things like motion, etc. And these need to be corrected through time so that basically we're not having an object that's kind of doing this the whole time, but instead is a singular kind of object, and we can focus on the things that change at the level of the neurons. And then a second step, and different programs and different people deal with this in different ways, but is to do something like slice time correction. And the reason for this is because in 2D imaging, we don't actually collect all of our slices at the same time. So if we're doing it kind of sequentially from bottom to top, well, that's not the example here, but we're kind of jumping around in space. We're actually collecting those at different times during the TR. And we often just group these as one singular block, as if they were all collected at the same time, but they're not. And so we need some kind of mechanism to actually line up the time series from different slices to make sure that they actually are kind of happening at the same time. And that's often some kind of interpolation mechanism. Next, we often do things like distortion correction. So this is basically taking our raw data and dealing with the fact that it doesn't always look exactly like our anatomicals. Sometimes it looks dramatically different than the anatomicals that we're trying to relate those to. And so we need some kind of mechanism to unwarp what our acquisition tool is actually giving us. And then frequently we want to actually convert whatever it is we have. And I highlight this specifically because I think a lot of our background is from 2D imaging, that we need to make sure that this is one block of data that we can then directly relate to the 3D acquisitions that we've been looking at in our anatomical data. And of course, once we do that, we need to make sure that we're actually aligning those two things properly. And then we often have the question of how do we deal with our statistics? How do we take advantage of the things that we have collected in a way that really gets us to the questions that we're asking in our science? So this can be things like denoising our signal. We're going to hear a little bit about denoising today. But specifically, a lot of the background that I've seen is our form of denoising is something like smoothing, either in time or in space or both. And then after all this is done, we're now ready to actually ask our questions. So we have these two things in the same space, the functional data and the anatomical data, and we might then want to look at some kind of volumetric relationship between them. So here we're showing an example of a task we're highlighting a particular part of the brain that changes over time based on that task. Okay, so then what changes in LAR fMRI? What gets more complicated? What is just relevant or not relevant? Well, the first thing is that I didn't even mention it because it's kind of almost ubiquitous, but the time series might not be bold when you're looking at LAR fMRI. We've looked at a lot of different contrasts to try to answer questions that are very, very specific to the hypotheses that we have about LAR function. So you may have things like spin echo or vaso signals or ASL, etc. There are many more examples that we could keep going with. Two, in motion correction, and we'll hear about this a little bit from John, it's not always the case that the out-of-the-box methods work perfectly, and sometimes we need a little bit of creativity when we're looking at really, really high resolution and sometimes relatively low contrast mechanisms in order to make sure that the two things that we're looking at, the anatomy, basically from functional image to functional image, how good are we aligning to each other? How can we make sure that this brain is not actually moving when we see a lot of different things happening? And I thought I added something here, but we might come back to it. But the point here is that not all of these types of motion are even related to the subject necessarily. Like yesterday, Renzo highlighted very specifically that oftentimes in 3D EPI, we might see field motion as one of our largest sources of motion. Okay, slice time correction. This can still be in play sometimes in layer fMRI. It depends on if you're doing 2D sequences, and oftentimes people are using multiband, which means that it's a little bit more complicated, but largely things stay the same. But frequently in layer fMRI, we're actually including 3D mechanisms. So 3D acquisitions don't really need slice time correction. They have a very different kind of temporal feature, which is that the whole image is actually collected over a series of time. So that's not relevant anymore. With distortion correction, and we'll hear about this a little bit later, distortion precision, or the correction of distortion correction, is really, really key, because we're often moving through the layers, and therefore we're actually moving them in a way that we need to make sure is okay. At the same time, denoising, we're going to hear a little bit about Nordic. This is a new feature to try to specifically get rid of thermal noise. But we also know about mechanisms of smoothing within the layers specifically. And so I'm just going to very, very quickly highlight kind of what this means for that little plot that we had at the beginning. So if the person is moving, it's very obvious that it's going to be very difficult to find our layer profiles, because as you can see on the right-hand side, the location of the anatomy in comparison to our functional, or the relationship between the two, is actually changing over time. And so if we just took the average of each of the X points along our little plot here, it would no longer look like the exact same thing. And this is in a case where there's absolutely no changes at all to the profiles. And at the same time, distortion is a very similar structure. This is actually a modification not where everything is moving the exact same amount, but that it's actually changing more over the different layers. So you can see that it spreads out across past the CSF. With denoising, this is a little bit more related to the functional activity that we're looking at. And this is just this is actually a really small amount of noise that we're adding to the profiles, but you can see that the chances of us seeing that exact structure that we saw at the beginning is a little bit more difficult here. I don't think we would get the idea that this is like two very distinct peaks. And then a little bit later on, we're going to actually hear about how do we think about this, where it's not the noise is the same across all different layers, but it's actually changing across different layers. So in this particular case, you can see that at the white matter border, we might see very little noise added, but as we go towards the CSF, we're actually getting more and more and more. And then lastly, we're also going to hear about partial volume effects. And I've tried to draw this as the relationship to the plots is on both axes, kind of, because basically it's a smoothing structure in both the location of the anatomy that we're looking at, and also how much functional contrast we're actually getting in every voxel. And so it's very hard to make interpretations, and the partial voluming effect is essentially trying to reverse that process. So again, this is our schedule for today, and I'll just leave it at that. If there are any really quick questions, that's great. Thank you so much.
Well, you're fielding questions. Any questions for Tyler?